All right, now for our third part of our lectures on sound waves. The last effect we want to talk about is the Doppler effect. It's one we've all heard. If you can think about a four-wheeler coming down the road and you're standing on the side of the road, you can hear it go from a high pitch to a low pitch as it passes you. That's the Doppler effect. The idea is, the principle of the idea is that the sound waves are part of the medium, and therefore the motion of either the source or the observer relative to the medium will affect what's heard by whatever the observer is. We usually talk about a source, a horn, and an observer. And so we've got a simulation out there on Canvas that'll let us look at that. So what we have here is we've got a motorcycle and a car, and the car is going to be the source, so it's going to sound his horn, and the motorcycle is going to be the observer, and we can move either one of them. And I think the first one that I wanted to do is run both for v equals 0, and then let the motorcycle move. So right now you can see the waves pulsing by, and whatever the emits, he hears. So the frequency he blinks at is the frequency he's hearing roughly. And so you can see the wave propagate through the medium. All right, now, if we let him move, then he's going to move toward the motorcycle, toward the car, and you can see that he's going to hit more waves because he's moving. Now, he's moving away, so he's going to hit the wave slower. He's going to blink not quite as slow, as fast, because when a wave travels, he's traveling too in the same direction, so it's like he's spreading it out. If we go toward the car, then he's going to pass him more frequently. He beeps quicker. Do that again. You can see he beeps quicker because the wave hits him. Oh, he got back to 0. A wave hits him, and then he moves toward it a little bit. So in effect, there's less distance between the two. All right, so the key is the wavelength. When we're looking at this effect, the distance, wavelength, remember, is the distance, the length of a wave, or peak-to-peak distance, or in what we're looking at, they're called our wave fronts. It's region of constant phase. The frequency is the number of wave fronts that passes the observer per second. It increased as the observer moves toward the source. The speed of the wave relative to the observer then is going to be v prime, is that speed is going to be the velocity of the observer plus the velocity of the wave. And in our equations, v will be the velocity of the wave, it's the sound velocity, and VO is the velocity of the observer. So effective increased velocity. So if you take that and plug it into, remember our formula for velocity equals frequency times wavelength? Well, if we solve that for wavelength, then we take the observed frequency over the actual wavelength, and the wavelength is the velocity over frequency. Rearrange it, you get that the frequency is going to be the velocity plus the velocity of the observer over v. And so that number is going to be bigger than 1, and you hear a high frequency if you're moving toward. Makes sense? We're moving toward it. We're passing the waves quicker than if we were moving away from it. And it does so by this ratio. Now, if the observer moves away, then he's actually stretching it out. So the difference is, what's important is the difference between his velocity and the velocity of the wave. You do the same math, only got a v minus v naught, and you'll end up with this, which says v minus v naught, velocity of the wave minus the observer, which is going to be less than 1. So you multiply it times f, you'll get a lower frequency. So we get a longer wave, lower frequency, higher frequency, shorter wave. And that's if the observer is moving. Now you can see that again in another simulation that we have, which again is available in Canvas. And here we're emitting the waves, nobody's moving, but this time the source is going to move. We could do that with the car too, but this one shows up nicely. So we've got two observers, and they're heard whatever the source emits. But if I let it move toward one of them, see how the waves are closer on that side and spread out further because it's moving? Now he's going to hear a higher frequency. Look, that's a sonic boom right there. We don't want to go that fast. But it's moving toward it. On the side toward, you've got a shorter wavelength, higher frequency. A side away, you've got a longer wavelength. You can see it here too. If we park him, reset, and let the car move, he blinks quicker. Or if we let him move back, he blinks slower, stretches out the wave. So both are nice visualizations to help you understand what we're seeing here. If you walk through the same type algebra that we did a minute ago, then you'll find that the observed frequency now works out to be velocity of sound in the medium minus the source. So that means you're dividing by a smaller number. Divide by a smaller number, you get a bigger number, and so we're going to have a bigger observed frequency. Same thing here, you plus, therefore that's a bigger number, divide by a bigger number, you get a smaller number. Smaller number times f will give us a lower frequency. Smaller number for frequency. Small number, lower, higher, high number, bigger. We can combine those into a single equation. This is the way I like to do it. I mean, you'll have, since we're doing a take-home test, you can, use either version that you like. But the way I do it is I've got them all here. Velocity of sound, observer, because they can all be moving, and source. And so, if we look here, I can actually, let's reset, I can have one moving that way and he moving that way. And we have both effects going on. We can turn him around. And so that single equation will capture both of those effects. Where if it's toward, you use the upper sign. If it's away, you use the lower sign. Now let's look at an example. A little summary there. Another picture. All right, suppose a sub, which is our source, is traveling at 8 meters a second, emitting at a frequency of 1400 hertz. The speed of the sound is 1533 underwater. The observer is traveling at 9 meters a second. Now we can draw a couple of different scenarios. And what we have to decide is who's moving which way. If they're approaching each other, and I'll do another example of this and draw it up a little better, but if they're approaching each other, then they're both approaching, you use both the upper signs, which in one makes that number bigger, that number smaller. And so you're going to take your initial, there's your velocity of sound, there's your velocity observer, there's your velocity of the source, 1400 hertz, 1416. So the net effect is a higher frequency. If they're moving away from each other, then you get both effects. Again, sound, observer, sound, source, original frequency, and you get one that's down. And I'll work some more examples and post them. But the videos, the simulations really is where it's at, where you can visualize the physics that's going on here by moving one versus the other and watching what the sound waves do. The sound waves do the same thing in the air. Their velocity is going to stay the same. All right. Well, take a look at some of those homework problems, and I'll post them where I worked it out and draw things up a little bit better in the attached homeworks. See you later.